Welcome back to another video. Let's jump right into the topic of conditional probability and independence. Conditional probability is the probability of an event occurring given that another event has already occurred. It allows us to update the probability of an event when we have additional information. The notation for conditional probability reads as the probability of A given B. The probability of A given B can be calculated as the ratio of the probability of A intersection B and the probability of B. Similarly, the probability of B given A can be calculated as the ratio of the probability of A intersection B and the probability of A. Given these formulas, we can see the probability of A intersection B can be calculated either by multiplying probability of event A by the conditional probability of B given A, or by multiplying probability of event B by the conditional probability of A given B. In probability, two events, A and B, are independent if the occurrence of one event does not affect the probability of the other. When A and B are independent, their relationship to conditional probability becomes straightforward. If two events, A and B, are independent, the conditional probability of A given B is equal to the probability of A happening. Similarly, the conditional probability of B given A is equal to the probability of B happening. It means that for independent events, A and B, having additional information about one of the events doesn't help us to better understand the other one. Events A and B are independent if the probability of their intersection is equal to the product of their individual probabilities. Let's go over an example together. Of the cars on a used car lot, we know 70% have air conditioning and 40% have a CD player. 20% of the cars have both. We want to find a few probabilities about this used car lot. You can pause the video here to take a moment and try answering these questions on your own. Let's go over an example together to see how to use basic probability rules and set theory to find these probabilities of interest. We have some information about the cars in a used car lot. We know that of the cars on a used car lot, 70% have air conditioning, 40% have a CD player, and 20% of the cars have both. We want to answer, what is the probability that a car has AC but no CD? For this question, we want to find the probability of cars that have AC and not have CD players, which translate to probability of AC intersection CD complement. This can be calculated as probability of cars having AC minus probability cars with AC intersection cars with CD players, equaling to 0.7 minus 0.2, which is equal to 0.5. What is the probability that a car has a CD player or AC, or both? Probability that a car has a CD player or AC, or both, is the probability of cars with AC union cars with CD players, which is calculated as 0.7 plus 0.4 minus 0.2, which is equal to 0.9. What is the probability that the car has no AC and no CD? Probability that the car has no AC and no CD refers to the complement probability of cars with AC union cars with CD players, which is equal to 1 minus 0.9, which is equal to 0.1. If a car has AC, what is the probability that it also has a CD player? This is the conditional probability of cars having a CD player given that those cars have AC, which is their intersection divided by the probability of the given, which is the probability of having AC. This is equal to 0.2 divided by 0.7, which is equal to approximately 0.28. If a car has a CD player, what is the probability that it also has AC? This is the conditional probability of cars having AC given that those cars have CD players, which is their intersection divided by the probability of the given, which is the probability of having CD players. This is equal to 0.2 divided by 0.4, which is equal to approximately 0.5. You can pause the video here to take a moment and try this game. There are 3 doors. Behind one door is a Lamborghini Aventador, the prize. Behind the other 2 doors are goats. You choose one door, say door 1. At this point, the chance of the Lamborghini being behind door 1 is January 3rd, and the chance it is behind one of the other 2 doors is February 3rd. The host, Monty, knows what's behind each door. Monty then opens one of the other 2 doors, say door 3, to reveal a goat. Monty now asks, would you like to stick with your original choice, door 1, or switch to the other unopened door, door 2? What would you do? Should you stay with your original choice or switch to the other unopened door to maximize your chances of winning? Here is the explanation. 1. Your initial choice. When you first pick a door, say door 1, the probability that the Lamborghini is behind door 1 is 1/3. The probability that the Lamborghini is behind one of the other two doors, doors 2 or 3, is 2/3. 2. Monty reveals a goat. Monty always opens a door with a goat. He does this to help you make a decision, but it doesn't change the probabilities you assigned at the start. 3. The effect of switching. If the Lamborghini was behind your original door, door 1, you lose by switching. If the Lamborghini was behind one of the other doors, doors 2 or 3, Monty's action of revealing a goat helps you know exactly which door to switch to, the one he didn't open. The probability of the Lamborghini being behind one of the other two doors is still 2/3, so by switching you take advantage of this higher probability. 4. Outcome. If you stick, your chance of winning stays 1/3. If you switch, your chance of winning becomes 2/3. Most people think the probability is 1/2 after Monty opens a door, because there are now only 2 doors left. However, this intuition ignores the fact that Monty's action is not random. He deliberately avoids the door with the Lamborghini. This intentional action skews the probabilities in favor of switching. Thank you for your attention, and see you in the next video.